All right, let's take a look at another one. Here's a question about potential difference. Question 15 asks, what is the total amount of work required to move a proton through a potential difference of 100 volts? So there's a little bit that you have to know here. You have to know what work is as a formula, of course, and you have to know that a proton is the same charge as an electron, which is 1.610 to the negative 19th of a coulomb. If you're not sure where to find that, that is right here on the reference table. One elementary charge is 1.6 times 10 to the negative 19th. If it's an electron, that's a negative value. If it's a proton, that's a positive value. So the potential difference, that's the V for volts, and it's 100 volts. So when we look at the math, it's very simple math. Here it is. We go to the standard definition of potential difference, which is the work done in moving a unit charge through an electric field. We solve this for W. So you have VQ or QV, depending on which text you're using, 100 volts times the actual charge, and when you multiply that out, you get 1.6 times 10 to the negative 17th joules. This is a little tricky because you really have a volt coulomb. A volt coulomb. Now, where did this joules come from? Work is in joules. That's why I said to you earlier, you have to remember the formula for work, which is a force times distance, but there's also an implication there. Newton times a meter, that's a force times a distance, and you get joules. So where do the joules come from? So joules is the unit that we use as a standard unit of work and energy. All right. So a volt coulomb is like the Newton meter in that it is replaced by the symbol for joules. 1 joule is needed to transfer 1 coulomb of charge from one point to another with a potential difference of 1 volt. So that's the definition of 1 joule of work and 1 joule of electrical work. All right, let's take a look at another one. Here's a problem about parallel plates. 2 oppositely charged parallel plates are 1 centimeter apart. They exert a force with a magnitude of 3.610 to the negative 15 newtons. That's your F value. On an electron. The minute they use the word electron, you know that it has a Q value, and it's on the front page of the reference table if you forget. It's placed between the plates. Calculate the magnitude of the electric field strength between the plates. So E is F divided by Q. The F was given as 3.610 to the negative 15, and the Q is 1.610 to the negative 19th of a coulomb. Interesting that they're not using a negative here, but they're just talking about the magnitude. See, the magnitude means the amount irregardless of the direction that it's being pulled. So they're giving you just a positive value, and you get newtons per coulomb. Let's take a look at another one. Here is problem 22, which is a discussion of the force on 2 electrons in a parallel plate field. The question asks, the diagram below represents 2 electrons, E1 and E2, located between 2 oppositely charged metal plates. Here's the plates. Which best describes the magnitude of the force exerted by the electric field on E1 compared to the magnitude of the force on the electric field on E2? So the key to this problem is to recall that in between electric plates, the key to this problem is to recall that the electric field between the 2 plates is uniform. It has the same force on each charge. Now, we also discussed the other day in another video that electric field points from positive to negative, but electrons go against the arrow because the arrow was designed on a positive test charge model. So since the electric field and the charges are the same, the force on both electrons is the same. This is problem 23, which is a rare question in the Regents catalog, asking about the field intensity and or the electric field strength on a point that's not exactly on a line in between them. So you have two metallic spheres, A and B, separated by a distance of 4 times 10 to the negative 1 meters. As shown in this diagram, the charge on each sphere is 1 microcoulomb. Point P is located near the spheres, so that's over here, which arrow best represents the direction of the resultant electric field at point P due to the charges on spheres A and B. So these are both positive charges, and so their electric fields point out and away. Point P is going to be pushed away from A in this direction. Point P is also going to be simultaneously pushed away from B in this direction. So the resultant of these two vectors is this blue vector. So point P has a charge placed on it, which would be accelerated away from it in this blue vector right here, up and away. And that's why it's choice 3. It's a tricky problem when they talk about the overlap of two fields. But now that you see the trick, it's the combination of the two fields resultant that is the direction of the field intensity at that point. Okay, let's take a look at another one. In the next question, we're asked which quantity of excess electric charge could be found on an object. This is a very simple kind of question. You basically are looking for the multiples of the value of 1.6. You can only have multiples of the charge. Here it is, excuse me. 1.6 10 to the negative 19. So what are the values of 1.6? 1.6 times 1, times 2, times 3, times 4, and so on. You can't have a fraction of a charge. So therefore, 1.6 10 to the 19 times 3 gives you 4.8 10 to the negative 19th coulombs. It's that simple. You look for a unit. Electric charge exists in whole units of charge. Only choice 2 is a whole unit multiple of the value of one elementary charge, seen right here.